the fastest object humanity has ever built, is screaming through space right now at 692,000 kilometers per hour, fast enough to cross from New York to Tokyo in under 60 seconds. Fast enough to outrun any bullet, any explosion, any force nature has ever thrown at this planet. And if you pointed it at the nearest star, just the closest one, just the neighbor next door, it would take 6,600 years to arrive. 6,600 years. That is the entire span of recorded human civilization. Every pyramid, every empire, every war, every revolution, every love letter ever written, every child ever born, all of it fits inside the travel time to one star. And there are 200 billion more just in our galaxy alone. But distance is only the first lock on the door. Behind it waits a speed limit woven into the fabric of reality itself, an energy cost that exceeds the mass of the observable universe, a biological death sentence that begins the moment you leave Earth's magnetic field, and a clock, Einstein's clock, that steals everyone you have ever loved while you sleep between the stars. We were told the universe was waiting for us, that the stars were destinations, that if we just built a better engine, a faster ship, a braver crew, we could touch the infinite. We were lied to, not by villains, by our own intuition, an intuition that evolved to judge the distance to a river, not the distance to a star. And tonight, that intuition breaks. 5 verdicts, 5 walls, 5 reasons the stars will never feel the weight of human footsteps. And by the time we reach the last one, you will understand something that changes the way you look at the night sky forever. This is the physics that makes interstellar travel impossible, and it begins now. You trust your gut. You have trusted it your whole life. It tells you when to brake in traffic. It tells you when someone is lying. It tells you when to duck, when to run, when to hold still. And most of the time, your gut is right. It kept your ancestors alive on the plains of Africa. It helped them judge the distance to a river, the speed of a predator, the weight of a stone in the hand. Your intuition is a survival tool, sharpened by millions of years of evolution, and it works beautifully on Earth. But tonight, we are leaving Earth, and the moment we do, that trusted gut feeling, that ancient compass inside your chest does not just become unreliable, it becomes dangerous, because it was never built for this. It was built for distances you can walk, and distances you can see with your eyes. Maybe, if you stretch it, distances you can fly in a metal tube at 30,000 feet. That is the limit. That is the edge of what your biology can truly feel and process. Beyond that edge, you are guessing. And in the cosmos, guessing is not just wrong, it is spectacularly, heartbreakingly wrong. Let me show you what I mean. You look up on a clear night, and you see stars, thousands of them. They look close. They look like they are scattered just above the treetops, like lanterns hung from an invisible ceiling. Your brain, doing its best, tells you that those lights are near, that they are part of your world, that if you could just build a tall enough ladder, you could reach out and touch one. This feeling is so strong, so deeply wired into your perception, that entire civilizations built their mythologies around it. The Greeks thought the stars were pinned to a crystal sphere. The Egyptians thought they were the souls of the dead just overhead, watching. Even today, when someone you love dies, people say they became a star, as if the stars are just up there, just a little beyond reach. They are not just beyond reach. They are beyond comprehension. And this is not a poetic exaggeration. This is a clinical, measurable, provable fact. The distances between stars are so enormous that your brain physically cannot hold them. Not because you are not smart enough, not because you did not study enough, but because the human mind evolved to navigate a world measured in footsteps, not light years. We can say the number, we can write it on a board, but we cannot feel it. And that gap between saying a number and feeling a number is where every dream of interstellar travel quietly goes to die. Consider the nearest star to our sun, just the neighbor, just the house next door in the cosmic suburb. Its name is Proxima Centauri, and it sits 4.24 light years away. Now, your brain hears 4 and relaxes. 4 is a small number. You have 4 fingers on one hand minus the thumb. You can count to 4 before your coffee gets cold. 4 sounds manageable. 4 sounds like a weekend trip. But a light year is not a unit your gut understands. A light year is the distance that light. The fastest thing in the known universe, the absolute cosmic speed limit, travels in 1 full year. Light moves at roughly 300,000 kilometers every single second. In 1 second, it could circle the Earth more than 7 times. In 1 year, it crosses about 9.5 trillion kilometers. And Proxima Centauri is 4.24 of those. Let that sink in, like cold water, down your spine. The nearest star, the closest one, the one right next door, is approximately 40 trillion kilometers away. 40 trillion. That is a number your mouth can say, but your mind cannot hold. If you started counting to 40 trillion, one number per second, without sleeping, without eating, without pausing, it would take you over 1.2 million years to finish counting. You would not be human anymore by the time you reach the end. Your species might not even exist. And here is where the gut truly snaps. The fastest object humanity has ever constructed is the Parker Solar Probe. It moves through space at nearly 692,000 kilometers per hour. That is fast enough to travel from New York to Tokyo in less than 60 seconds. It is so fast that if you could see it pass, you would not see it. It would be gone before the light from its surface reached your eye. This is the pinnacle of human velocity. The absolute fastest we have ever thrown anything into the void. If you strapped yourself to that probe and aimed it at Proxima Centauri, if you launched today with all the fury of human engineering behind you, you would arrive in approximately 6,600 years. Let me say that differently, so you feel the weight. If the ancient Egyptians, the ones who stacked the Great Pyramids stone by stone under the boiling sun, if they had launched this probe on the day they laid the final capstone, that probe would only just now be arriving at the nearest star. 4,500 years of pharaohs, empires, plagues, revolutions, world wars, the invention of language, writing, electricity, computers, the internet. All of that history fits inside the travel time to one star. The closest star, the one next door. And there are roughly 200 billion stars in our galaxy alone. And there are roughly 2 trillion galaxies in the observable universe, had each one filled with hundreds of billions of their own stars. The numbers are not just large, they are hostile. They are designed, it seems, to mock every ambition we have ever had about crossing the void. So when you look up tonight and see those tiny lights, those gentle twinkling dots that seem so close, so reachable, so inviting, I want you to hold this truth gently in your hands. Your gut lied to you. It told you the stars were near. They are not near. They are so far away that the very concept of distance begins to lose meaning. Like a word you repeat so many times, it dissolves into nonsense on your tongue. And yet, we dream. We dream of going there. We dream of warp drives and wormholes and sleek silver ships cutting through the black. And those dreams are beautiful. They are the best of us, but the universe does not grade on beauty. It grades on physics. And physics, as we are about to discover, is merciless. The scale is only the beginning. Because beyond the distance, beyond the raw emptiness between the stars, there waits a deeper truth. A wall built not of stone or steel, but of the very fabric of reality itself. And no engine, no fuel, no civilization, no matter how advanced, has ever found a door in that wall. Let us climb. Let us build a ladder in the mind, rung by rung, and see how quickly the familiar world shrinks beneath our feet. Because the only way to truly grasp why interstellar travel breaks every rule we know is to feel the scale in your bones. Not as a number on a page, but as a sensation, a vertigo, a slow, creeping realization that the universe was not built for visitors. Start where you are, right here, on the surface of a planet called Earth. It is a sphere roughly 12,742 kilometers across. That sounds big, and it is, for a human. You could spend your entire life exploring its mountains, its oceans, its hidden valleys and frozen poles, and you would never see it all. Earth feels infinite to someone walking on foot, but from space, from even a modest altitude, it is a marble, a pale blue marble hanging in nothing. An astronaut on the International Space Station sees the whole thing in a single glance. The continents look like smudges. The oceans look like puddles. Everything you have ever known, every city, every war, every love story, every empire fits on that marble. And the marble is small. Now step back further. Move away from Earth and look at our solar system. The sun sits at the center, a burning sphere so large that you could fit 1.3 million Earths inside it. And between the sun and our little blue world, there stretches a gap of 150 million kilometers. Light, that tireless cosmic messenger, takes 8 minutes and 20 seconds to cross it. If the sun vanished right now, blinked out of existence like a candle in the wind, you would not know for over 8 minutes. You would still feel its warmth on your skin. You would still see its light in the sky. For 8 long minutes, you would live in a lie, warmed by the ghost of a dead star. That is how wide just our little neighborhood is. But the solar system does not end at Earth. It does not even end at Mars or Jupiter or Saturn with its golden rings. The solar system stretches out to the Oort cloud, a vast shell of icy debris that surrounds us like a frozen halo. The outer edge of the Oort cloud sits roughly 2 light-years from the sun. 2 light-years just to leave our own front yard. And most people do not even know it exists. We think of the solar system as a neat little diagram with 8 planets in a row, but the truth is far stranger and far larger. The diagram in your school textbook was a comforting lie. The real solar system is mostly empty space, a cathedral of nothing, with a few specks of rock and gas scattered through it like dust in a sunbeam. Now we step beyond, out past the Oort cloud, into the interstellar medium, the space between stars, and here is where the ladder begins to groan under the weight of reality. Because this space is not like the space between cities or countries. It is not like the space between Earth and the Moon. It is a void so absolute, so perfectly empty, that it contains on average about 1 atom per cubic centimeter. 1 atom. In a space the size of a sugar cube, there is almost nothing. No air, no sound, no warmth, just silence and distance stretching in every direction like an ocean with no shore. We already know that Proxima Centauri, the nearest star, sits 4.24 light-years away. We already felt the weight of that number, 6,600 years at our fastest speed. But Proxima Centauri is just the first porch light on a street that stretches beyond imagination. Let us keep climbing the ladder. The next nearest star system is Barnard star, about 6 light-years away. Then Wolf 359 at roughly 7.8 light-years. Then Leyland 21,185 at 8.3. These are all neighbors. These are all close by galactic standards. And yet each one would take thousands upon thousands of years to reach with anything we have ever built. We cannot even visit our neighbors, let alone cross the city. And the city is the Milky Way galaxy, our home. A vast spiral of stars, gas, dust, and dark matter that stretches 100,000 light-years from edge to edge. 100,000 light-years. Let that number wash over you like a wave you cannot swim against. If you wanted to cross the Milky Way at the speed of the Parker Solar Probe, the fastest thing humanity has ever made, the journey would take over 150 million years. That is longer than the entire age of mammals on Earth. Dinosaurs would still roam the planet when you launched, and by the time you arrived at the other side, evolution would have reshaped every living thing beyond recognition. You would not just be crossing a galaxy, you would be outliving entire branches of the tree of life. And here is the thought that some scientists whisper about late at night, the speculative edge that few textbooks mention. Some physicists have wondered whether the sheer scale of the universe is not just a feature, but a purpose, not designed by a mind, but emergent from the laws themselves. The distances between stars may act as a kind of quarantine, a natural firewall that keeps civilizations apart. Not out of cruelty, but out of necessity. Because if every intelligent species could easily reach every other, the chaos might be unmanageable. The universe, in its vastness, may be protecting itself from its own children. This is not proven. This is not mainstream. But it haunts the edges of the conversation like a ghost you cannot quite see. And still, we have not left our own galaxy. The Milky Way, enormous as it is just one galaxy among roughly 2 trillion in the observable universe. The nearest large galaxy, Andromeda, is 2.5 million light-years away. At the Parker Solar Probe speed, that trip would take billions of years. Billions. The word has lost all meaning at this point. It is just a sound your mouth makes while your brain quietly surrenders. The observable universe itself stretches 93 billion light-years across, and beyond that boundary, there may be more universe, perhaps infinitely more, that we will never see because the light from those regions has not had time to reach us since the Big Bang. We are inside a bubble of visibility, and the walls of that bubble are racing away from us faster than light itself, carried by the expansion of space. There may be wonders out there, civilizations, structures, phenomena beyond our wildest imagination, and we will never, ever know. Not because we are not clever enough, but because the universe itself has drawn a curtain that no technology can pull aside. This is the ladder of scale, and we have climbed it as high as language allows. Below us, Earth has vanished. The sun is a faint dot. The Milky Way is a smudge. And all around us, in every direction, the darkness stretches on forever, filled with light that left its source before our species existed and will arrive at its destination long after we are gone. The distance alone should be enough to humble any civilization, but the universe is not finished. Because even if you could somehow cross these impossible gulfs, there is a wall waiting for you at the edge of speed itself. A wall that does not bend, does not break, and does not care how advanced you are. There is a number that governs everything. It does not negotiate. It does not make exceptions. It does not care if you are a human in a tin can or a godlike civilization that harvests the energy of entire galaxies. That number is 200, and 99,792.458 kilometers per second. The speed of light. And it is not just a speed, it is the law. Most people think of the speed of light the way they think of the sound barrier. There was a time when engineers said we could never fly faster than sound. Pilots tried, and their planes shook apart. The air fought back. It seemed impossible. And then Chuck Yeager climbed into the Bell X, one in 1947, and punched through it like a fist through wet paper. Boom. Done. The sound barrier was an engineering problem, and we solved it with better engineering. So, naturally, people look at the speed of light and think the same thing. We just need a bigger engine, a better fuel, a cleverer design. Give us time, and we will break this barrier too. This thinking is completely, fundamentally wrong, and understanding why it is wrong changes everything about how you see the universe. The sound barrier was a wall made of air. It was a physical challenge in a physical medium. The speed of light is not a wall made of anything. It is a wall made of reality itself. It is woven into the fabric of space-time, into the geometry of existence. It is not that nothing can go faster than light. It is that faster than light has no meaning. It is like asking what is north of the North Pole. The question itself breaks down. The words stop working. The concept dissolves. Einstein showed us this in 1905 with his special theory of relativity. And the math is as beautiful as it is brutal. Here is what happens when you try to go fast. Really fast. In your daily life, speed is simple. You push a car, it moves. You push harder, it moves faster. Double the force, double the speed. This is how your gut understands motion. It is linear. It is clean. It is wrong. It works at low speeds, at human speeds, because the error is so small you cannot notice it. But as you approach the speed of light, the error grows monstrous. When an object moves, it carries kinetic energy. The faster it moves, the more energy it carries. At normal speeds, this relationship is straightforward. But as you approach that cosmic speed limit, something strange and terrifying happens. The energy you pour into the ship stops making it faster and starts making it heavier. Not heavier in the way you feel after a big meal. Heavier in a way that warps the mathematics of motion itself. Physicists call this relativistic mass, and it increases without limit as you approach light speed. Think of it like pushing a boulder up a hill that gets steeper the higher you climb. At first, the slope is gentle and you make good progress. But with every step, the hill tilts more, and more, and more, until eventually the hill is vertical and you are pushing a boulder that has become infinitely heavy against a slope that has become infinitely steep. You will never reach the top. Not because you are weak, but because the top does not exist in any way your muscles can reach. To accelerate a single object with mass, even something as small as a grain of sand, to exactly the speed of light would require infinite energy. Not a lot of energy. Not the energy of a star or a galaxy or a billion galaxies. Infinite energy. And infinite is not a big number. Infinite is the place where numbers stop existing. There is not enough energy in the entire observable universe to push one grain of sand across that final threshold. You can get close. You can get to 90% of light speed if you have extraordinary resources. You can get to 99% if you burn fuel on a scale that dwarfs anything humanity has ever imagined. You can even get to 99.9999% if you are willing to spend the energy output of entire star systems. But that last fraction, that final sliver between almost and actually, is an infinite wall. You will approach it forever and never touch it. And here is what makes this even more haunting. The speed of light is not just a speed limit for ships, it is the speed of causality. It is the maximum rate at which any event in the universe can influence any other event. When you flip a light switch, the signal does not travel from the switch to the bulb instantly. It travels at the speed of light. When gravity pulls you toward the Earth, that gravitational information travels at the speed of light. When you see a star explode in a distant galaxy, you are seeing it, not as it is, but as it was, because the light took millions of years to reach your eyes. This means that if something could travel faster than light, it could arrive before it left. Effects could happen before causes. You could see the glass shatter before it was pushed off the table. The entire structure of cause and effect, the thing that allows history to exist, the thing that allows logic to function, would collapse. The universe would become meaningless noise. So the speed of light is not just a rule about how fast you can go. It is the rule that holds reality together. Now, there is a strange loophole that physicists love to debate, and it lives on the speculative edge of known physics. Space itself can expand faster than light. During the first moments after the Big Bang, in a period called cosmic inflation, the universe expanded at a rate far exceeding light speed. Galaxies at the edge of the observable universe are right now moving away from us faster than light, carried by the expansion of space itself. This does not violate Einstein, because nothing is moving through space faster than light. Space itself is stretching, carrying everything with it, like dots on a balloon being inflated. Some theorists, most famously Miguel Alcubierre in 1994, proposed a hypothetical warp drive that would exploit this principle. Instead of moving a ship through space, you would compress space in front of the ship and expand it behind, essentially surfing on a wave of space-time. The ship itself would not move faster than light within its local bubble, but the bubble would carry it across vast distances at effectively superluminal speeds. It is a beautiful idea. It is also, as far as we can tell, impossible. The Alcubierre drive requires exotic matter with negative energy density, something that has never been observed, may not exist, and if it did, would require quantities so vast that the energy demands circle back to the same old wall. Infinite, or near enough to infinite, that the difference does not matter. The speed of light is not a challenge waiting to be overcome. It is a verdict, a final, unappealable verdict handed down by the deepest structure of reality. And every civilization in every galaxy, no matter how old, no matter how brilliant, lives under that same verdict. But even if you accept this wall, even if you agree to travel at a fraction of light speed, to crawl across the void at the fastest pace physics allows, there is another horror waiting for you. A horror that twists the very nature of time itself and turns every journey into a one-way ticket to a future where nothing you loved still exists. So you accept the wall. You accept that light speed is the absolute limit, the ceiling of the cosmos that no amount of cleverness can shatter. Fine. You are practical. You say, we will travel at 90% of light speed, or 80%, or even 10%. We will be slow pilgrims in a vast cathedral. We will take our time. We will endure the years, the decades, perhaps even the centuries. We will cross the void not with brute force, but with patience. And the universe says, very well. But there is a price, and the price is time. Not time the way you think of it. Not the steady ticking of a clock on your kitchen wall, where every second is the same length as the last. Out there, near the speed of light, time becomes something slippery, something treacherous, something that flows differently depending on how fast you are moving. And this is not science fiction. This is measured fact. This is confirmed by experiments so precise they can detect the difference in time between a clock on the ground floor and a clock on the top floor of a building. Einstein called it time dilation, and it is one of the most beautiful and most devastating truths in all of physics. Here is how it works. When you move through space, you also move through time. But there is a strange trade-off between the two. The faster you move through space, the slower you move through time. At normal speeds, walking, driving, flying, the effect is so tiny that it is invisible. A few billionths of a second over an entire lifetime. You would never notice. But as you approach the speed of light, the effect grows enormous. At 90% of light speed, time on your ship runs at roughly half the rate of time back on Earth. For every year that passes on your ship, about 2.3 years pass on Earth. You feel a year. Your family feels more than 2. Now scale that up. At 99% of light speed, the ratio becomes even more extreme. For every year on the ship, roughly 7 years pass on Earth. At 99.9%, the ratio climbs higher still. Time on your ship slows to a crawl, while back home, decades, centuries, millennia race by like pages in the wind. This sounds like a gift at first. If time slows down for you, then you can survive longer journeys. A trip to a star 50, light years away at 99% of light speed might only feel like 7 years to you on the ship. 7 years. That is manageable. That is a long deployment, a prison sentence, a doctoral program. You could endure 7 years, but here is the cruelty that hides inside the gift. While 7 years pass for you, 50 years pass on Earth. You arrive at the distant star, you plant your flag, you look back toward home, and everyone you left behind is old. Your children have grey hair. Your partner has lived a whole life without you. Your friends have died. The world you knew has changed so completely that it might as well be a different planet. You did not just travel through space. You traveled into the future. A future where you are a stranger. A future where your name is a memory, fading from the minds of people you once held close. And there is no coming back. Even if you turned around immediately and flew home at the same speed, the same dilation would apply. More years would vanish from the world you knew. By the time you returned, a century might have passed on Earth. Everything would be different. The language might have shifted. The governments might have fallen. The cities you grew up in might be ruins or museums or parking lots. You would step off the ship as a living fossil, a relic from a dead era, younger than your own great-grandchildren. This is not theoretical. This is proven. In 1971, physicists Joseph Haffel and Richard Keating put atomic clocks on commercial airplanes and flew them around the world. When they compared the flying clocks to identical clocks that stayed on the ground, the flying clocks had fallen behind by a tiny but measurable amount. Time had literally passed more slowly for the moving clocks. At airplane speeds, the difference was billionths of a second. At near light speed, the difference would be lifetimes. GPS satellites experience this effect every single day. They orbit Earth at high speed, and their clocks tick slightly slower than clocks on the ground. If engineers did not correct for time dilation, your GPS would drift by about 10 kilometers per day. You would end up in the wrong city. The correction for Einstein's time dilation is not a theoretical curiosity. It is a daily practical necessity that makes your phone work. So imagine a civilization that decides to send explorers to a distant star. They build the ship. They recruit the bravest souls. They say goodbye. And the travelers leave, accelerating to some large fraction of light speed. From the traveler's perspective, the journey might take 10 years, 20 years, maybe 50. Painful but survivable. But from the perspective of the civilization that sent them, centuries pass. Governments rise and fall. Technologies transform. The very language evolves until the messages the travelers send back home sound like ancient poetry, beautiful but incomprehensible. And this creates what some thinkers call the paradox of the returning stranger. Even if you could make the trip, even if your body survived and your ship held together, the home you left would no longer exist. Not because it was destroyed, but because time devoured it in your absence. You would be a time traveler, but only in one direction, forward, into a world that does not know you and does not need you. There is a strange and speculative edge to this that physicists still debate quietly in conference hallways and late-night conversations. If time dilation is real, and it is, then a traveler moving at extreme speeds is essentially skipping forward through the timeline of the universe. Some theorists have wondered whether an advanced civilization might use this deliberately, not as a bug but as a feature. Launch yourself at near light speed, let millions of years pass on the outside, and arrive in a future where the universe itself has changed. New stars have formed, old ones have died, perhaps new civilizations have risen. You would be a time capsule, a message in a bottle thrown not across space but across eons. It is a haunting thought, and no one knows if anyone has ever tried it. But whether you use time dilation or suffer from it, the result is the same. Interstellar travel is a one-way door. You can leave, but you can never truly come home. The place you loved will be gone long before you return. And this cruel mathematics leads us to yet another wall, perhaps the most practical and most punishing wall of all. Because even before you wrestle with time, even before you face the loneliness of the returning stranger, you have to answer a much simpler question. Where do you get the fuel? Every dream of crossing the stars eventually crashes into the same wall. Not the wall of distance, not the wall of time. Something far more mundane, far more embarrassing. The gas tank. Because you can dream all you want about distant suns and alien worlds. You can sketch warp drives on napkins and argue about time dilation over coffee. But at some point, someone has to sit down and ask the simplest, most devastating question in all of space travel. How much fuel do we need? And the answer, every single time, is too much. Far, far too much. This is the tyranny of the rocket equation, and it has been crushing dreams since 1903. That was the year a Russian schoolteacher named Konstantin Tsiolkovsky, working alone, without funding, without a laboratory, scribbled down an equation that would quietly define the limits of space travel for all of human history. The equation itself looks simple. It fits on a single line. But hidden inside that single line is an exponential curse so vicious that it turns every ambition into absurdity. Here is what the equation says, in plain language. To move a ship, you need fuel. But fuel has weight. So to move the fuel that moves the ship, you need more fuel. But that extra fuel also has weight. So you need even more fuel to carry the extra fuel that carries the original fuel. And that additional fuel has weight too. So you need more fuel to carry that. And on and on and on, spiraling upward in an exponential loop that grows faster than any straight line, faster than any budget, faster than any supply chain in the universe. At small scales, this is manageable. When you fly from London to New York, the airplane carries enough fuel to make the trip, and the weight of the fuel is a significant but solvable problem. Engineers design around it. They make the plane lighter. They make the engines more efficient. It works because the distances are small and the speeds are modest. But when the distances become interstellar and the speeds become relativistic, the rocket equation does not just become difficult, it becomes insane. Let us try a concrete example. Suppose you want to send a ship to Proxima Centauri, the nearest star, and you want to get there within a single human lifetime, say 40 years. To do that, you need to accelerate to a meaningful percentage of the speed of light. Let us say 10%. That is 30,000 kilometers per second. Incredibly fast, unimaginably fast, but achievable in theory. Now here is the part that everyone forgets. You do not just need to speed up, you also need to slow down. When you arrive at Proxima Centauri, you cannot just fly past it at 10% of light speed. You need to decelerate, you need to brake, and braking in space means firing your engines in the opposite direction for just as long and just as hard as you did when you sped up. Which means you need to carry all the fuel for the braking maneuver with you from the very beginning. You need to accelerate that braking fuel across 4 light years before you even use it. And the fuel to accelerate that fuel. And the fuel to accelerate that fuel. The exponential curse spirals into madness. If you do the math using our current best chemical rockets, the kind that burn liquid hydrogen and liquid oxygen, the amount of fuel required to send a modest ship to Proxima Centauri within a human lifetime is not large. It is not enormous. It is not even astronomical. It exceeds the mass of the entire observable universe. Every star, every planet, every grain of dust, every black hole, every photon of light in the entire cosmos would not be enough fuel to make the trip with chemical rockets. The number is so absurd that it loops past tragedy and lands somewhere near comedy. This is why rocket scientists do not sleep well at night. The equation is not broken. The equation is perfect. The universe is simply that demanding. Now you might wonder about what scientists call the mass ratio. This is the ratio between the total mass of the ship when fully loaded with fuel and the mass of the ship when empty. For a trip to the moon, the mass ratio is manageable. The Saturn V rocket that carried astronauts to the moon had a mass ratio of about 25:1, 25 kilograms of fuel and rocket for every 1 kilogram that actually reached the destination. That is expensive but doable. For an interstellar trip at 10% of light speed, the mass ratio climbs into numbers that have no physical meaning. You would need a ship that is almost entirely fuel, a flying gas tank the size of a mountain range, carrying a payload the size of a suitcase. And this is not a problem that clever engineering can solve. It is not about building better rockets or finding lighter materials. It is about the fundamental relationship between energy and mass, written into the laws of physics by nature itself. The rocket equation does not care about your ambition. It does not care about your funding. It simply multiplies over and over until the numbers become monsters. There is an open debate among aerospace engineers and physicists that rarely reaches the public. Some argue that the rocket equation essentially proves that no civilization anywhere in the universe can achieve interstellar travel using any form of onboard propulsion. The logic is simple and cold. If you carry your fuel with you, the exponential curse applies. It does not matter what fuel you use: chemical, nuclear, antimatter. The exponential always wins. The only way to escape the tyranny would be to not carry your fuel at all, to somehow push the ship from the outside, using lasers or solar sails, or something we have not invented yet. But even these ideas, as we will explore, carry their own impossible price tags. The rocket equation is the universe's way of saying, you can dream about the stars, but you cannot afford the ticket. And the cruelest part is that this equation applies to every civilization in every galaxy. An alien species 1 billion years older than us, with technology that would look like magic to our eyes, still lives under the same exponential curse. They still have to carry fuel. They still have to fight the mass ratio. they still have to answer the same devastating question. How do you move fuel that is heavier than the ship it is supposed to carry? The answer, as we are about to discover, is that you look for better fuel. You look for the most powerful energy sources in the universe. And you find that even the most powerful energy sources in existence are not powerful enough. So the rocket equation has cornered us. Chemical rockets are laughable for interstellar travel. The fuel requirements exceed the mass of the observable universe. Fine. We are clever creatures. We will find better fuel. We will climb the energy ladder rung by rung and search for something powerful enough to break the exponential curse. Surely somewhere on that ladder there is a fuel source potent enough to carry us to the stars. Let us climb and see. The first step above chemical rockets is nuclear fission. This is the energy that powers nuclear reactors and nuclear bombs. It works by splitting heavy atoms like uranium, releasing the energy that binds their nuclei together. Fission is roughly 1,000,000 times more energy dense than chemical fuel. A kilogram of uranium contains as much energy as 3,000 tons of coal. That sounds extraordinary, and for many purposes it is. But for interstellar travel, it is still pitiful. A fission-powered ship heading to Proxima Centauri would still need a fuel mass thousands of times greater than the ship itself. The mountain of fuel shrinks compared to chemical rockets, but it is still a mountain. And uranium is heavy, radioactive, and difficult to handle. You are essentially building a flying nuclear reactor and hoping nothing goes wrong for 40 years straight. The next rung on the ladder is nuclear fusion. This is the energy of the sun. Instead of splitting heavy atoms, you smash light atoms together, hydrogen into helium, and the energy released is staggering. Your fusion is roughly 4 times more efficient than fission per unit of mass, and the fuel, hydrogen, is the most abundant element in the universe. It sounds perfect. There is just one small problem. We cannot do it yet. After 70 years of research, billions of dollars in funding, and some of the most brilliant minds in human history working on the problem, we have not yet achieved sustained, controlled nuclear fusion on Earth. We have built reactors that can sustain fusion for a few seconds. We have achieved brief moments of net energy gain, but a working fusion power plant that produces reliable, continuous energy remains decades away. And a fusion engine powerful enough and light enough to propel a starship is so far beyond our current abilities that it borders on fantasy. But let us pretend. Let us grant humanity the gift of perfect fusion technology. Even then, the math is grim. A fusion-powered starship heading to the nearest star at 10% of light speed would need to be almost entirely fuel. Engineers have sketched designs like Project Daedalus, a theoretical fusion starship designed by the British Interplanetary Society in the 1970s. Daedalus would have been a 2-stage spacecraft weighing over 50,000 tons at launch, carrying 50,000 tons of fusion fuel pellets made from helium-3, a rare isotope found in trace amounts on the Moon. The payload, the actual scientific instruments and equipment it would deliver, would weigh only 450 tons. The ship would be 99% fuel and 1% purpose, a flying gas tank the size of a skyscraper, delivering a payload the size of a modest building. And Daedalus was designed for a one-way flyby, not stopping, not orbiting, not landing. Just screaming past Barnard's star at 12% of light speed and snapping a few photographs before vanishing into the void forever. That is the best fusion can offer. A one-way ticket to a glimpse. So let us climb higher. The next rung is antimatter. And this is where the dreams become truly intoxicating. Antimatter is the mirror image of normal matter. For every particle, there exists an antiparticle with the same mass but opposite charge. When matter meets antimatter, they annihilate each other completely, converting 100% of their combined mass into pure energy. This is the most efficient energy conversion possible in physics. Nothing else comes close. A single gram of antimatter reacting with a gram of normal matter would release the same energy as the Hiroshima bomb. 1 gram, the weight of a paperclip. If you could fill a tank with antimatter, you would have the most powerful fuel source in the known universe. A few kilograms could theoretically propel a small ship to a nearby star. The rocket equation would still apply, but the numbers would finally become almost manageable, almost within reach, almost possible. But antimatter has a problem. Several problems, actually, each one more devastating than the last. First, we cannot make it in useful quantities. Antimatter is produced in particle accelerators, one atom at a time, in collisions that require enormous energy. CERN, the largest particle physics laboratory on Earth, produces roughly 1/1000th of a gram of antimatter per year. At that rate, to produce a single gram of antimatter, enough to fuel perhaps a small probe, would take roughly 1 billion years. The entire energy output of the human civilization for millions of years would need to be dedicated to antimatter production, just to fill a modest tank once. Second, antimatter is almost impossible to store. It annihilates on contact with any normal matter. You cannot put it in a bottle. You cannot pour it into a tank. You must suspend it in a perfect magnetic vacuum, using powerful magnetic fields to keep it from touching the walls of its container. The slightest failure, a power glitch, a micrometeorite puncture, a tiny fluctuation in the magnetic field, and your fuel tank explodes with the force of a nuclear weapon. Third, even if you solved production and storage, the cost is beyond comprehension. Current estimates suggest that producing 1 gram of antimatter would cost roughly $62 trillion. That is more than the gross domestic product of every nation on Earth combined. For 1 gram, a starship might need tons. There is one more idea that lives on the speculative fringe, and it sidesteps the rocket equation entirely. Instead of carrying fuel, what if you pushed the ship from behind using lasers? This is the concept behind Breakthrough Starshot, a real project funded by physicist Yuri Milner. The idea is to build a tiny sail, perhaps a few meters wide and thinner than a human hair, attach a microchip-sized probe, and blast it with a ground-based laser array so powerful that it accelerates the sail to 20% of light speed. No fuel on board, no rocket equation. The ship carries nothing but a camera and a transmitter. It is brilliant in concept, but the laser array would need to generate roughly 100 gigawatts of power, equivalent to the entire electrical output of a large nation, focused on a target the size of a bedsheet for about 10 minutes. The engineering challenges are extraordinary, and the probe, if it works, would be so small and so fast that it could not stop at its destination. It would fly past Proxima Centauri in a matter of hours, snapping a few images before hurtling into the eternal dark, never to return. Every fuel, every propulsion method, every clever workaround leads to the same conclusion. The universe has priced interstellar travel so high that even the most advanced imaginable civilizations would pause and ask whether it is worth the cost. And even if they decided to pay that cost, even if they burned a star's worth of energy to launch a single ship, they would still face a passenger that refuses to cooperate. The human body. You have survived the distance. You have accepted the speed limit. You have somehow, through some miracle of engineering or magic, solved the fuel problem. Your ship is built, your engines hum with power, the stars await. there is just one final passenger to load. You, a human being, a sack of water and protein and electricity, balanced on two fragile legs, wrapped in thin skin, powered by a fist-sized pump that beats 100,000 times a day without being asked. And this passenger, this beautiful, improbable, extraordinary machine called the human body, is about to become the weakest link in the entire chain. Because the human body was not designed for space. It was designed for one very specific world. A world with a particular gravity, a particular atmosphere, a particular magnetic shield, a particular temperature range. Remove any one of those and the body begins to fail. Remove all of them, which is exactly what space does, and the body begins to die. Let us start with the most immediate killer: radiation. On Earth, you live inside a bubble of protection that you never think about. The planet's magnetic field, generated by the churning liquid iron core deep below your feet, stretches thousands of kilometers into space and deflects the worst of the cosmic radiation that constantly bombards us. Without this invisible shield, life on Earth would have been sterilized long ago. You walk around every day bathed in safety, and you have no idea how rare and precious that safety is. The moment you leave Earth's magnetic field, the safety ends. You are now exposed to the full fury of the cosmos. Cosmic rays, which sound poetic but are actually terrifying, are high-energy subatomic particles moving at nearly the speed of light. Protons, helium, nuclei, and heavy ions like iron, all screaming through space with energies that dwarf anything we can produce in our most powerful particle accelerators. These particles do not just hit your skin. They pass through the hull of your ship like it is not there. They pass through your body. And as they pass through, they leave a trail of destruction. A single heavy cosmic ray particle can tear through a strand of DNA like a bullet through a spider web. It does not just break the strand, it shatters it into fragments, creating double-strand breaks that are the hardest type of DNA damage for your cells to repair. And when your cells fail to repair this damage correctly, the result is mutation. Cancer. On a trip to Mars, which takes roughly 7 months, astronauts face a measurably increased lifetime cancer risk. NASA has studied this extensively and considers radiation one of the primary obstacles to deep space travel. Now imagine, not 7 months, but 7 years, or 70, or 700. On a journey to another star, the cumulative radiation dose would be staggering. Every cell in your body would be hit again and again, year after year. Your DNA would accumulate damage faster than it could repair. Cancer would not be a risk, it would be a certainty. But your body would become a garden of tumors, blooming silently in the dark between the stars. You could add shielding, lead, water, concrete, hydrogen-rich polymers. All of these absorb some radiation, but shielding is heavy, desperately heavy. To provide meaningful protection against cosmic rays, you would need meters of dense material surrounding the entire crew compartment. And every kilogram of shielding feeds back into the rocket equation. More mass means more fuel. More fuel means more mass. The loop of doom tightens once again, and radiation is only the beginning. Because even if you solve the shielding problem, there is another assassin waiting inside the ship, one that requires no particles, no impact, no external threat at all: gravity, or rather, the absence of it. In zero gravity, the human body dissolves. Not dramatically, not in a burst of flame or a spray of blood. Quietly, slowly, like a sandcastle in a gentle rain. Your bones, which on Earth are constantly rebuilding themselves in response to the stress of carrying your weight, begin to thin. Without gravity pulling on them, they see no reason to stay strong. Astronauts on the International Space Station lose roughly 1 to 2% of their bone density per month. After 6 months, they return to Earth with the bones of an elderly person. After a few years, those bones would become so fragile that a stumble could shatter them. Your muscles waste away for the same reason. Without gravity to push against, they atrophy. Your heart, which is a muscle, shrinks. It becomes lazy. Why pump hard when there is no gravity to fight? Your cardiovascular system, designed for a world where blood must be pushed upward against gravity, becomes confused. Fluid shifts toward your head, causing your face to puff up and your sinuses to clog. Your eyes deform. Astronauts on the ISS have reported permanent vision changes caused by increased pressure inside the skull. Some have returned to Earth needing glasses for the first time in their lives. After 6 months in space, astronauts come back weakened, disoriented, and physically aged. It takes months of rehabilitation to recover. And these are astronauts who spent 6 months in low Earth orbit, still partially protected by Earth's magnetic field, with regular supply shipments and immediate medical support. Imagine a journey of 600 years. Imagine generations born and raised in zero gravity, their bodies adapting to weightlessness in ways we cannot predict. Their bones would be paper. Their hearts would be whispers. They would be so physically transformed that they could never set foot on a planet with real gravity. They would be prisoners of their own ship forever. There is a speculative idea that some biologists have quietly discussed. What if long-duration spaceflight does not just weaken the human body, but fundamentally changes it? Not through technology or genetic engineering, but through natural selection. Over enough generations in zero gravity, bathed in radiation, isolated in a closed environment, the human body might evolve. Not into something stronger, but into something different. Something adapted to the ship, but utterly alien to Earth. The descendants of the original crew might be recognizably human in outline, but profoundly different in structure. Thinner bones, larger heads, weaker limbs, altered immune systems. They would be a new species, born not on a planet, but in a metal tube between the stars. This is the betrayal of biology. Your body is the software of Earth, exquisitely tuned, magnificently calibrated, perfectly adapted to one tiny world. Take it anywhere else, and it crashes. Not with a dramatic error message, with a slow, silent decay that eats you from the inside out while you float in the dark, dreaming of a home your bones can no longer support. But perhaps there is a way around this, and perhaps we do not need to keep the body alive for the whole journey. Perhaps we can freeze it, pause it, put it to sleep, and wake it up when we arrive. Or perhaps we can let generations live and die on the ship, passing the mission forward like a relay baton across centuries. These ideas sound reasonable. They sound hopeful. They are neither. The body betrays. We know this now. So the dreamers pivot. They look for shortcuts around biology. And two ideas rise above all others, glittering with promise, shimmering with the false light of hope. Cryosleep and generation ships. One says we freeze the passengers and wake them at the destination. The other says we let them live and die on the ship, passing the mission to their children like an inheritance. Both ideas are beautiful in science fiction. Both are nightmares in science fact. Let us start with cryosleep. The idea is seductive in its simplicity. You cool the body down, slow all biological processes to a halt, and essentially press pause on life itself. The traveler sleeps through the centuries of the voyage, unaware of the passing time, unaged, preserved like a butterfly in amber. When the ship arrives at the distant star, the crew is thawed, awakened, fresh and ready to explore. It is the backbone of 100 movies. It is clean. It is elegant. It is also, as far as current science can tell, Impossible. Here is the problem. Your body is roughly 60% water. Every cell in your body contains water. And when water freezes, it does something catastrophic. It expands. And as it expands, it forms crystals. Not beautiful snowflake crystals. Tiny, jagged, sharp crystals that act like microscopic daggers. These ice crystals puncture the cell membrane, the thin wall that holds each cell together. They shred the delicate internal structures, the mitochondria, the nucleus, the endoplasmic reticulum, names you may have forgotten from biology class, but structures your life depends on every second. When you freeze a living cell, you do not preserve it. You destroy it from the inside out. This is why you cannot freeze a strawberry and thaw it back to its original form. It comes out mushy, soft, broken. The cell walls have been shattered by ice. Now imagine doing that to a human brain. Billions of neurons, each one connected to thousands of others by synapses so fine they make spider silk look like rope. Freeze those connections and the ice crystals sever them. Your memories, your personality, your consciousness, all stored in the precise architecture of those neural connections, would be shredded into biological noise. You would not wake up, so you would thaw into something that was once a person. There is a technique called vitrification that scientists have explored. Instead of freezing the body slowly, which allows large ice crystals to form, you cool it extremely rapidly while pumping it full of cryoprotectant chemicals, essentially biological antifreeze. The goal is to turn the water in the cells into a glass-like solid without forming crystals. This works on tiny samples, individual cells, thin slices of tissue, small organisms. But scaling it up to an entire human body is a problem of a completely different order. The cryoprotectants themselves are toxic in the concentrations needed to protect a full human body. And ensuring uniform cooling throughout an object as large and complex as a person, and making sure the brain cools at the same rate as the liver, the heart, the fingertips, is a challenge that no one has come close to solving. Some researchers in the field of cryonics believe it will eventually be possible. Companies already exist that will freeze your body after death, hoping that future technology will be able to repair the damage and revive you. Hundreds of people lie in metal tanks right now, suspended in liquid nitrogen at minus 196 degrees Celsius, waiting for a resurrection that may never come. It is an act of faith dressed in the language of science. And the honest truth is that no one knows if the damage done by freezing is reversible. The information that made you who you were may simply be gone, scattered like letters from a book thrown into a blender. You can still see the letters, but the story is lost. So cryosleep, for now and perhaps forever, remains a myth. A beautiful, comforting myth. But a myth. Which brings us to the second idea. The generation ship. If you cannot freeze the passengers, let them live. Build a ship large enough to sustain a community. Fill it with farms, with water recyclers, with artificial lighting and air scrubbers, and schools and hospitals. Let the first generation launch from Earth knowing they will never arrive. Their children will not arrive either, nor their grandchildren. But someday, generations later, the descendants of the original crew will step off the ship and onto a new world. The mission spans centuries. The ship becomes a world unto itself, a tiny metal civilization sailing through the dark. It sounds heroic. It sounds noble. It sounds like the kind of thing humanity should attempt. But it also sounds like someone who has never met humans. Put 500 people inside a metal cylinder. Seal the doors. Tell them they can never leave. Tell them their children can never leave. Tell them that the destination is so far away that no one alive on the ship will ever see it. Now wait 500 years and see what happens. Social structures will fracture. They always do. Every closed community in human history has experienced internal conflict, power struggles, factions, and fragmentation. The ship will need governance, but who governs? The captain's descendants? An elected council? A religious order? Within a few generations, the original mission will become mythology. The people on the ship will not remember Earth as a real place. It will become a legend, a creation, myth, a story told to children who were born in a metal hallway and have never seen a sky. Language will drift. Isolated communities develop distinct dialects within a few generations. After 500 years, the people on the ship might speak a language incomprehensible to anyone on Earth. Their culture will evolve in ways no one predicted. Their values will shift. Their relationship to the mission itself will change. Some will want to continue. Some will want to turn back. Some will want to stop the ship and declare it their permanent home. Conflict is inevitable. And then there is genetics. Of 500 people is a dangerously small gene pool. Geneticists call this a population bottleneck, and it leads to inbreeding over time. Recessive genetic disorders become more common with each generation. Genetic diversity decreases, making the population more vulnerable to disease. After enough generations, the health of the community could deteriorate significantly. The people who finally arrive at the distant star might be physically and genetically compromised, weakened by centuries of isolation in a closed genetic system. There is a haunting thought experiment that some ethicists have raised about generation ships, one that rarely gets discussed publicly. Is it moral to condemn your unborn descendants to life inside a metal box? The first generation chose to board the ship. They volunteered, but their children did not. Their grandchildren did not. Every subsequent generation is born into a prison they never chose, carrying a mission they never agreed to, heading toward a destination they may not want. It is an inheritance of obligation without consent. Some philosophers argue that a generation ship would be the largest act of imposed destiny in human history. So, cryosleep shatters the cells. And generation ships shatter the society. Biology cannot be paused, and humanity cannot be contained. The body refuses to be frozen, and the mind refuses to be caged. Every biological shortcut leads to the same dead end. But perhaps the answer is to remove biology from the equation entirely. Perhaps the travelers should not be human at all. Perhaps they should be machines. Cold, patient, radiation-resistant machines sailing through the void without needing food or air or companionship. Surely silicon can go where flesh cannot. The answer, as always, is more complicated than the hope. So we abandon the body. We leave flesh behind. We say, fine, humans cannot survive the journey. The radiation is too fierce, the gravity too absent, the time too long, the freezing too destructive, the social pressures too crushing. We accept all of this, and we turn instead to machines, robots, artificial intelligence, silicon minds that do not breathe, do not eat, do not get lonely, do not get cancer, do not care if 1,000 years pass in the dark. Surely this is the answer. Surely this is how you cross the void. It is a reasonable thought, and at first glance, machines seem like the perfect interstellar travelers. They do not need oxygen. They do not need water. They do not need farms or schools or therapists. They do not suffer existential crises when they realize everyone they loved is dead. They can be powered by small nuclear reactors that run for decades. They can be built from materials far more durable than bone and skin. They can carry the sum of human knowledge in a hard drive the size of your thumbnail. They are patient in a way that no biological creature can ever be. But the universe does not play favorites. It does not spare machines from its cruelty just because they are made of metal instead of meat. And the deeper you look at the challenges facing a machine on an interstellar journey, the more you realize that silicon has its own set of fatal weaknesses. Different from biology's weaknesses, but just as deadly over the timescales we are talking about. The first enemy is the same one that threatens human travelers: radiation. Cosmic rays do not just damage DNA, they damage electronics. When a high-energy particle strikes a computer chip, it can flip a bit, changing a 1 to a 0 or a 0 to a 1. This is called a single event upset, and it happens all the time, even in low Earth orbit. The International Space Station experiences these bit flips regularly. On Earth, our atmosphere and magnetic field absorb most cosmic rays before they reach our computers. In deep space, there is no such protection. A single flipped bit might sound harmless. What is one wrong digit among billions? But in a computer controlling a starship, one wrong bit can corrupt a navigation calculation, alter a course correction, crash a program, or trigger a cascade of errors that propagates through the entire system. Over thousands of years of exposure to cosmic radiation, the cumulative effect would be devastating. The ship's computers would slowly go mad, corrupted bit by bit, error by error, until the software that controls everything from propulsion to communication to basic housekeeping becomes unreliable. And there is no one to reboot the system. No technician, no repair crew, no genius bar in the interstellar void. You can build redundancy into the system. Multiple copies of every program, error-correcting codes that detect and fix corrupted data, backup processes that take over when primary ones fail, and all of these help, but they do not eliminate the problem. They delay it. Over a long enough timeline, and interstellar timelines are very, very long, even the most robust error correction systems will be overwhelmed. Entropy always wins. Given enough time, every system degrades, every backup fails, every redundancy is exhausted. The second enemy is physical. The ship itself is made of matter, and matter, over long periods, does something inconvenient. It falls apart. Metal fatigues, joints loosen, seals degrade, lubricants evaporate, circuits corrode. The slow, patient chemistry of oxidation and material stress works on every component of the ship, year after year, century after century. On Earth, we deal with this by replacing parts, by maintaining machines, by building new ones when old ones wear out. In deep space, thousands of years from the nearest spare part, maintenance is impossible. Engineers have considered self-repairing machines, ships that carry raw materials and manufacturing equipment, able to fabricate replacement parts on the fly. This is a real concept studied under the name von Neumann probes, after the mathematician John von Neumann, who first described self-replicating machines. The idea is elegant. The ship carries a factory. The factory can build anything the ship needs, including copies of itself. In theory, such a probe could repair itself indefinitely, even replicate and spread to multiple star systems. But building a self-replicating machine that can operate autonomously for thousands of years without any external input is a challenge so far beyond our current capabilities that it might as well be magic. The machine would need to mine raw materials from asteroids or planets it encounters along the way. It would need to smelt, refine, and manufacture components with the precision of a modern semiconductor fabrication plant. It would need to diagnose its own failures, design solutions, and implement repairs, all without human guidance. We cannot even build a dishwasher that lasts 20 years without breaking. The idea of a self-maintaining starship that functions flawlessly for millennia is, at present, pure fantasy. And then there is the third enemy, the one that strikes without warning, without mercy, and without any possible defense. Micrometeoroids. Space is not perfectly empty. It is filled with tiny particles, grains of dust, fragments of rock, shards of ice, with debris from ancient collisions and long-dead comets. These particles are small. Most are no larger than a grain of sand. On Earth, a grain of sand is harmless. You brush it off your skin without a thought. But in space, everything is moving. And when your ship is traveling at even a modest fraction of the speed of light, the relative velocity between the ship and these tiny particles becomes extraordinary. A grain of sand hitting your ship at 10% of the speed of light carries kinetic energy comparable to a hand grenade. A particle the size of a pea would hit with the force of a bomb. And there is no way to see them coming. They are too small to detect at range. They are too fast to dodge. They simply appear like invisible bullets fired from the darkness, and they punch through your hull, through your circuits, through your instruments, leaving trails of destruction that accumulate over time. There is a speculative and deeply unsettling calculation that some physicists have performed. At 10% of light speed, even the sparse hydrogen atoms floating in the interstellar medium, just 1 or 2 atoms per cubic centimeter, would create a constant bombardment against the ship's front surface. Each individual impact is negligible, but over years and decades, the cumulative effect is like flying through an invisible sandstorm. The hull erodes, the sensors degrade, the front of the ship slowly ablates away, worn down by the relentless friction of nearly empty space. So even machines, those patient, tireless silicon pilgrims we placed all our hope in, face a gauntlet of destruction that stretches across millennia. Radiation corrupts their minds, time corrodes their bodies, dust shreds their skin. And entropy, that quiet universal law that says all order eventually crumbles into disorder, works patiently against every bolt, every wire, every circuit, every line of code. The galaxy is wider than any warranty, and no machine yet imagined could survive the crossing intact. Not because we are not clever enough to build one, but because the universe has set the journey's length beyond the lifespan of any material we know. Yet suppose, against all odds, against every physical law we have discussed, that someone out there has solved every problem. They have crossed the distance. They have beaten the equation. They have survived the radiation and the dust and the time. Why then have we not heard from them? Why has no signal reached us? Why is the sky so silent? The answer lies not in space, but in time. And it is perhaps the saddest verdict of all. We have walked through distance, through speed, through fuel, through flesh, through silicon. We have watched every solution crumble under the weight of physics. But let us set all of that aside for a moment. Let us be generous. Let us imagine that somewhere out there, a civilization solved every problem we have discussed. They beat the rocket equation. They shielded their bodies or their machines from radiation. They found a fuel source powerful enough to carry them across the void. They are out there, right now, alive, intelligent, curious. Why have we not heard from them? This is the question that haunts astronomy. It is called the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked it over lunch in 1950. If the universe is so vast, so old, or so filled with stars and planets, where is everybody? The math says they should exist. The silence says they do not. Or at least, they do not exist in any way we can detect. And the answer, the one that cuts deepest, has nothing to do with technology or intelligence. It has to do with time, the most merciless dimension of all. The universe is 13.8 billion years old. Let that age settle into your mind. 13.8 billion years. In that incomprehensible span, stars have been born, have burned for billions of years, and have died. Galaxies have formed, collided, merged, and reformed. The chemical elements that make up your body were forged in the cores of stars that exploded before our sun even existed. The universe has been busy for a very, very long time. Now consider humanity. We have existed as a species for roughly 300,000 years. We have been technological, capable of sending and receiving radio signals for about 120 years. 120 years out of 13.8 billion. If you compressed the age of the universe into a single calendar year, starting with the Big Bang on January 1st, humanity's entire technological civilization would occupy the last fraction of a second before midnight on December 31st. We are not even a blink. We are the pause between blinks. And this is the devastating mathematics of asynchronous civilizations. Civilizations do not appear at the same time. They do not last forever. They rise, they burn brightly for a cosmic instant, and then they fall. But maybe they destroy themselves. Maybe they exhaust their resources. Maybe they evolve into something unrecognizable. Maybe they simply fade, like embers in a fire that no one tends. Whatever the reason, civilizations are temporary. And in a universe this old and this large, the chances of two temporary civilizations existing at the same time, in the same region of space, at the same technological level, are vanishingly small. Think of it this way. Imagine a dark forest stretching endlessly in every direction. In this forest, there are fireflies. Each firefly blinks once, just once, and then goes dark forever. One blinks on a Tuesday evening. Another blinks on a Friday morning, 3,000 years later, on the other side of the forest. They never see each other, not because the forest is empty, but because the blinks do not overlap. This is the universe we live in. Civilizations are fireflies. They blink once in the darkness of cosmic time and vanish. A civilization may have thrived near Proxima Centauri 1 billion years ago. They may have built cities and written symphonies and wondered if they were alone. But they are gone now. Their radio signals faded into noise millions of years before our sun even formed. Another civilization might arise there 1 billion years from now, long after humanity has become a fossil record on a forgotten planet. The tragedy is not that the universe is empty. The tragedy is that the guests keep arriving at different times to a party that never ends but never overlaps. And even if two civilizations did exist at the same time, communication would still be nearly impossible. We have been broadcasting radio signals for about 100 years. Those signals travel at the speed of light, expanding outward from Earth in a growing sphere. That sphere is now roughly 100 light-years in radius. In the context of the Milky Way, which is 100,000 light-years across, our signal bubble is a tiny dot. A microscopic whisper in a hurricane. For someone to hear us, they would need to be within that bubble, listening on the right frequency, pointing their instrument in exactly our direction at exactly this moment. The cosmic haystack problem makes this almost impossible. There are billions of stars to search, billions of frequencies to monitor. The sky is enormous and the signals are weak. Our television broadcasts and radio chatter, which we sometimes romantically imagine echoing across the galaxy, actually fade into undetectable noise within a few light years. The inverse square law is ruthless. Signal strength drops with the square of the distance. By the time our signals reach even the nearest stars, they are fainter than the background radiation of the universe itself. We are not shouting into the void. We are whispering, and the void is not listening. There is a thought that some researchers at the SETI Institute have raised, one that lives on the speculative edge of the field. What if civilizations go silent on purpose? Not because they are destroyed, but because they learn that broadcasting your presence into an unknown universe is dangerous. This is sometimes called the dark forest theory, inspired by science fiction but grounded in game theory. If you do not know the intentions of other civilizations, and you cannot know because the communication delay is measured in centuries or millennia, then the safest strategy is to stay quiet, hide, listen, but never speak, because any signal you send reveals your location, and you have no way of knowing who is listening or what they might do with that information. Under this theory, the universe might be teeming with civilizations, all of them silent, all of them hiding, all of them watching the darkness with wide eyes and closed mouths. The silence would not mean emptiness. It would mean fear. It is a chilling thought, and while it remains speculation, it is logically consistent with everything we observe, which is nothing at all. But whether the silence is caused by time, by distance, by the fading of signals, or by deliberate hiding, the result is the same. We are alone in practice, even if we are not alone in principle. The universe may be full of life, full of intelligence, full of wonder, but it has arranged itself so that none of those lives can touch each other. Each civilization is an island, surrounded not by water but by light years and centuries and the crushing indifference of physics. And yet, despite all of this, despite every verdict we have explored, people still point to the sky and say, "But what about the UFOs? What about the videos? What about the lights that move in ways no known aircraft can move?" Surely that is proof that someone has beaten the physics. Surely that is evidence that the impossible has been achieved. It is time to address those lights, and to do so, we will need everything we have learned so far. We have spent a long time in the dark together. We have climbed the ladder of scale and seen the distances that mock our ambitions. We have hit the wall of light speed and watched our dreams flatten against it. We have drowned in the rocket equation and choked on the cruelty of time dilation. We have watched the body betray, the ice crystals shred, the generation ships fracture, and the silicon pilgrims corrode. We have seen the fireflies blink in the darkness and miss each other by millennia. And now, after all of that, someone shows you a grainy video filmed from a Navy jet, a blurry shape, a smudge of light, an object that seems to move in ways that defy explanation. And they say, "See, aliens are already here. Let us take a breath and let us apply everything we have learned." The most famous of these videos emerged from the United States military between 2017 and 2020. The Pentagon itself acknowledged them. Fighter pilots described objects that accelerated from a standstill to extraordinary speeds in an instant, that changed direction without any visible means of propulsion, that hovered without wings or rotors, and that seemed to operate without any regard for the laws of aerodynamics. These accounts are sincere. These pilots are trained observers. They are not lying. They saw something they could not explain. But there is an enormous difference between something I cannot explain and something that requires aliens who traveled 10,000 light years to explain. The gap between those two statements is wider than the Milky Way itself. Let us start with the physics. The videos show objects that appear to accelerate from 0 to speeds estimated at Mach 20 or higher in less than a second. Let us think about what that means. Acceleration that rapid would generate thousands of g-forces. At those levels, the effects on matter are absolute and unavoidable. Metal liquefies. Electronics flatten into useless sheets of silicon. Any biological pilot inside, regardless of species, regardless of home planet, would be instantly reduced to a thin red film on the back wall of the cockpit. This is not speculation. This is Newtonian mechanics. Force equals mass times acceleration. At thousands of g-forces, no known material, biological or mechanical, can maintain structural integrity. Whatever is in those videos, if it is truly accelerating that fast, it is not carrying passengers. Now consider the atmosphere. An object moving at Mach 20 through Earth's atmosphere is not a quiet event. At those speeds, the air itself cannot move out of the way fast enough. It compresses violently in front of the object, creating a shock wave that we experience as a sonic boom. Every object that exceeds the speed of sound in our atmosphere produces this boom. There are no exceptions. It is a consequence of fluid dynamics, as reliable as gravity. But the objects in these videos produce no sonic boom. None. No shock wave, no thunder. Just silent movement through the sky. Furthermore, at Mach 20, the friction between the object and the atmosphere would heat the air around it to thousands of degrees. The nitrogen and oxygen molecules in the air would be ripped apart, creating a glowing trail of plasma that would light up the sky like a second sun. This is exactly what happens when a meteor enters the atmosphere. You see a blazing trail across the sky because the air itself is being torn apart by the speed. The objects in the videos show no plasma trail, no ionization, no glow, no atmospheric disruption of any kind. They just move, silently, cleanly, impossibly. This means one of two things. Either these objects have somehow cancelled out every known law of aerodynamics, thermodynamics, and Newtonian mechanics simultaneously, or they are not actually doing what they appear to be doing. And this is where the boring explanation enters the room. Camera artifacts, sensor glitches, parallax effects, infrared glare from rotating gimbals, birds and balloons seen through instruments designed to track fast-moving military targets. These explanations are not exciting. They do not make good headlines. They do not get millions of views on social media. But they are consistent with the physics we know to be true. One of the most famous Navy videos, the so-called gimbal video, shows an object that appears to rotate smoothly against the sky. Independent analysis by optical engineers has shown that the rotation is consistent with the behavior of infrared glare as the camera's gimbal mechanism rotates. The object is not rotating. The camera system is creating the illusion of rotation. It is a lens artifact, not a spacecraft. Another video, known as Go Fast, appears to show an object screaming across the ocean's surface at incredible speed. But when you account for the altitude of the jet, the angle of the camera, and the parallax effect caused by the jet's own movement, the object's actual speed is consistent with a large bird or a balloon drifting in the wind. It looks fast because of the camera geometry, not because it is fast. This is not conspiracy. This is optics. This is how cameras work. And the human brain, that same gut instinct we discussed at the very beginning of our journey, desperately wants to see something extraordinary. It wants the blurry shape to be a spacecraft. It wants the mystery to be profound. Confirmation bias is one of the most powerful forces in human psychology. We see what we want to see, and we interpret ambiguous data in the direction of our hopes. Now let us apply the bigger picture. Suppose aliens truly were visiting Earth. Suppose they had conquered every physical barrier we have discussed. They had crossed thousands of light years, burned incomprehensible amounts of energy, solved the rocket equation, survived radiation and micrometeoroids and the corrosion of time. They arrived at Earth with technology so advanced it would appear as magic to our eyes. Why would we be seeing them on grainy infrared cameras? A civilization with that level of energy output would be impossible to miss. The physics of their arrival would light up every instrument on the planet. The energy required to decelerate a starship from interstellar velocity would release radiation detectable from across the solar system. You would not need a blurry video to prove their existence. Every telescope, every radio dish, every particle detector on Earth would be screaming at once. Their presence would be as obvious as the sun, and yet, the only evidence offered is shaky footage from military cameras. Footage that trained optical engineers can explain with mundane physics. Extraordinary claims require extraordinary evidence. This is not a slogan. It is a principle of reasoning that has served science for centuries, and blurry videos, no matter how many of them there are, no matter how sincere the witnesses, are not extraordinary evidence. They are ordinary evidence of ordinary phenomena filtered through extraordinary hopes. There is a deeper philosophical point here that some skeptics have raised, one that rarely gets the attention it deserves. The desire to believe in alien visitors may itself be a kind of religious impulse dressed in technological clothing. Throughout history, humans have looked to the sky for saviors, gods, angels, divine messengers. The alien visitor is the modern version of this ancient longing. Someone out there, someone wiser, someone more powerful, is watching over us. They will come. They will save us. We are not alone. It is a beautiful wish, but physics does not grant wishes. Physics grants facts. And the facts, as we have walked through them tonight, are unforgiving. The distances are too vast. The speeds are too limited. The energy costs are too extreme. The biology is too fragile. The time windows are too narrow. But this does not mean the story ends in despair. Because there is one more thing to see. One more truth waiting at the end of all this darkness. And it is not a verdict. It is a gift. We have walked a long road together through the dark. We have measured the distances and felt them stretch beyond comprehension. We have pressed our hands against the wall of light speed and felt it refuse to move. We have watched the rocket equation devour every dream with its exponential hunger. We have seen the body dissolve in the absence of gravity, the cells shatter under ice, the societies fracture inside metal cans, and the machines corrode under the patient hand of entropy. We have watched the fireflies blink and miss each other across billions of years. We have held the blurry videos up to the light of physics and watched them dissolve into glare and parallax. And now, at the end of all these verdicts, you might expect despair. You might expect me to say that the universe is cruel, that existence is pointless, that we are prisoners on a rock with nowhere to go and no one to meet. But I am not going to say that, because the truth, the real truth that hides behind all this darkness is something far more extraordinary than any alien visit could ever be. The silence is not a tragedy. The silence is a revelation. Think about what the speed of light actually does. Yes, it traps us. Yes, it prevents us from crossing the galaxy in a weekend. But it also does something else. Something essential. Something without which nothing. Not you, not me, not the stars, not life itself could exist. The speed of light preserves causality. It ensures that causes come before effects. It guarantees that the universe has a logical sequence, a history, a story that unfolds in order. Without that speed limit, effects could happen before their causes. You could see a glass shatter before it was pushed. You could die before you were born. Time itself would become meaningless noise, a jumble of events with no sequence and no sense. The same laws that imprison us are the laws that allow us to exist. The speed of light is not a wall built to frustrate us. It is a wall built to protect the structure of reality itself. And every civilization in every galaxy benefits from that protection. even as they chafe against its limits. And think about what the distances actually mean. Yes, they prevent us from visiting other stars, but they also create something precious: isolation, safety, room to grow. If every civilization in the galaxy could easily reach every other, the result would not be a peaceful federation of enlightened beings sharing poetry and recipes. It would more likely be chaos, competition, conflict. The same evolutionary pressures that drive species to compete for resources on a single planet would scale up to a galactic level. The distances between stars may function as a kind of natural quarantine, not cruel but wise, giving each civilization the space to develop on its own terms, at its own pace, without interference or invasion. The universe, in its vastness, may be protecting its children from each other. And now, consider what this means for Earth. In a universe where interstellar travel is effectively impossible, where no one is coming to save us or conquer us, where the silence is real and permanent, Earth becomes something extraordinary. Not a truck stop on a galactic highway, not a minor colony in a vast empire, not a curiosity to be studied by passing travelers. Earth becomes singular, precious, perhaps unique in ways we cannot yet measure. Life exists here. Consciousness exists here. A species arose from the dust of ancient stars, learned to ask questions about the nature of reality, built telescopes to peer into the void, and developed mathematics precise enough to understand why the void cannot be crossed. That is not a failure. That is a miracle. That is the universe becoming aware of itself through a collection of atoms that somehow learned to wonder. The carbon in your bones was forged in the core of a dying star billions of years ago. The iron in your blood was created in a supernova explosion so violent that it briefly outshone an entire galaxy. The hydrogen in the water that makes up most of your body has existed since the first moments after the Big Bang, 13.8 billion years ago. You are not separate from the cosmos. You are the cosmos, arranged into a temporary pattern that can ask questions about its own origin. And we are not stopping the search. We are simply getting smarter about it. The old dream of shaking hands with an alien in a cantina has given way to something more mature, more patient, more scientific. We are looking for techno-signatures, the fingerprints that a technological civilization might leave on the light of its star. We are searching for the infrared excess that a Dyson sphere would produce, the waste heat of a civilization that has enclosed its sun. We are scanning for laser pulses, narrowband radio signals, chemical anomalies in the atmospheres of exoplanets that might indicate industrial activity. We are listening to the universe not with the frantic desperation of a child lost in a shopping mall, but with the quiet discipline of a scientist who understands that the answer, if it comes, will come slowly and in whispers. And perhaps the answer will be silence. Perhaps we will search for 1,000 years and find nothing. Perhaps the fireflies never overlap. Perhaps we are truly, permanently, cosmically alone. And if that is the case, then the responsibility falls entirely on us. There is no alien cavalry coming over the hill. No advanced civilization is going to descend and fix our climate, resolve our conflicts, cure our diseases, or teach us to be wise. We are the only minds we know of in the entire observable universe, the only ones asking questions, the only ones capable of understanding the answers. That is not a burden. That is a privilege beyond measure. So the next time you step outside on a clear night and look up at the stars, do not feel small. Do not feel crushed by the distances or defeated by the physics. Feel the weight of what you are. You are a living thing on a tiny rock, looking out at an ocean of fire and emptiness, and you understand it. Not fully, not yet, but better than anything else we know of in the entire cosmos. You are the universe's way of knowing itself. And for now, in this brief shining moment between the birth of stars and the death of stars, that is enough. The verdicts stand. Distance, speed, energy, biology, time. They are absolute. They are merciless. They are beautiful. And within their boundaries, within the cage of physics that holds us gently on this pale blue dot, something impossible happened anyway. You happened. And now, let the stars keep their distance. Let the silence continue its ancient watch. Let the void stretch on in every direction, cold and vast and indifferent. You are warm. You are here. You are awake. And the very fact that you understand why the stars are unreachable makes you more remarkable than any spaceship that could ever reach them. Let your breath slow now. Let the weight of these numbers, these distances, these impossible scales settle softly around you like a blanket woven from starlight. You do not need to carry them. You do not need to solve them. You only need to rest, knowing that somewhere in the darkness, the same physics that keeps the stars apart is also holding your atoms together, keeping your heart beating, letting your eyes close. The universe is silent, but you are not. You are its voice, its question, its wonder. Rest now. The stars will wait.